Hi, I'm Gary Jordan. We're here at the NASA Johnson Space Center in Houston, Texas. And this is the space vehicle mock-up facility where we have full-scale mock-ups of all the habitable modules on the International Space Station. Astronauts come here and they train for emergency situations and to learn some of the systems that are on the International Space Station. And behind me is a mock-up of BEAM, the Bigelow Expandable Activity Module. And this is a mock-up of the actual module that is attached to the International Space Station right now. It's compressed on the International Space Station, and in 2 days it's going to inflate to 4.5 times its size. And we're really excited. This is a milestone. This is the first time a human-rated expandable module has been up in space. And with me, I have two very special guests who know everything there is to know about the Bigelow Expandable Activity Module, Rajib Dasgupta and Lisa Kauke. So, since we're on Facebook Live, sending your questions to the comment section below. I'll be monitoring them from my phone right here, and we'll have the experts here answer some of the questions. So why don't we start by you guys introducing yourselves and what your role in BEAM is.
Yeah, thanks. Good afternoon. I'm Rajib Dasgupta, and I am part of the NASA Research Integration Office, and my role is the project manager for the Bigelow Expandable Activity Module project. Lisa?
And I'm Lisa Kauke from Bigelow Aerospace, and I'm the Deputy Program Manager for the BEAM project. And I started working as an engineer on the program 3 years ago, so I've had the chance to see this from start to finish.
All right, so I see the comments are already starting to fly in. We'll try to get to as many of them as we can. We're expecting to do about a 30-minute broadcast today. But why don't we start by just talking about what BEAM is just in general? Can we start with just that?
I'll let Lisa start off.
Sure. So BEAM is a technology demonstration of an expandable module, and our company has been working on expandables since the early 2000s. And this is our first chance for an expandable to interact with humans on orbit, so we're really excited. And the advantage of launching an expandable to space is the packing factor. In other words, it packs down really small in the launch vehicle, and it saves on mass, but most importantly, volume. And then once it gets on orbit, it expands. So BEAM actually expands quite a lot. It went up in the SpaceX Dragon trunk, and it was about 3 feet internally, and it expands to be about 9 feet internally. So that internal volume, the empty space inside, increases by about 11 times. And then the outside volume increases about 4 times. So you can see how we get a lot of advantages from launching an expandable.
That's awesome. And the Dragon cargo vehicle launched to the International Space Station on April 8th. The robotic arm of the International Space Station grabbed the capsule on April 10th, and the BEAM module was actually installed on the International Space Station April 16th. And now we're just waiting for its expansion in 2 days. So we have a question on Facebook Live from Greg. How is it protected from micrometeoroid impacts?
Well, that's a great question, and that's actually something we love to talk about because our debris shield is just as good, if not better, than the debris shielding that's on station. So essentially it's a stack of layers of material, and if a piece of orbital debris strikes, it shatters it there and it keeps it from penetrating all the way through.
And I would add to that we have tested all the International Space Station modules with something what we call hypervelocity impact that simulates the orbital debris environment, and we've done the same identical testing on BEAM, and its performance is equal or better than the existing space station metal modules.
And we're talking about the strength of the layers that are in the BEAM module, correct?
Yes.
Awesome. So this is a question from Dustin. How is it doing on the International Space Station right now? Kind of what does it look like, I guess, compared to what we're looking at right now?
Lisa, you want to describe that?
Well, this is the expanded configuration, and on orbit right now it's in its packed configuration, so it's a lot smaller. It's actually about a third the length, and it looks actually kind of more like flower petals on the outside, and you'll see those expand, and so that should be pretty neat to see. It has a lot of layers that move.
Awesome. So while we're here, why don't we talk about the history of expandable modules in space? Where did this all start and how is it right now with Bigelow?
I'll take a shot at that. So the history of expandables with NASA dates back to the early 90s, and the NASA Johnson Space Center actually, we took a project called TransHab, and we worked on the TransHab project till the late 1990s. And then we learned a lot from that project, but unfortunately, beginning of 2000, Congress canceled that project due to funding reasons. And at that point, Mr. Bigelow, who is the president of Bigelow Aerospace, had a lot of interest in expandables, and he purchased the NASA patent on that on that expandable technology and started working on developing commercial inflatables. And Bigelow Aerospace actually have sent 2 demonstration units for expandables, the Genesis 1 and 2 in 2006 and 2007, and they performed really, really well. And they're still up on orbit, although we're not getting any active data out of them right now. And then after that, in the late 2012 timeframe, Bigelow sent us, NASA, a proposal for a joint NASA industry partnership to send an expandable module on International Space Station. So the whole purpose is to learn from the experience of certifying an expandable to a human-rated ISS spacecraft. And since 2012, we have been developing the module working in partnership with Bigelow Aerospace. Of course, they have done the entire design and development, and we on the NASA side have done the entire integration to the ISS. And so here we are, ready on ISS to be expanded.
All right, so this is going to be expanded on Thursday, 4:30 a.m. Central Time, 5:30 a.m. Eastern, and you can watch it live on NASA TV. We have a question from Daniel. What happens when it expands, and how do you keep it expanded in space?
Repeat the question.
What happens when it expands?
Okay.
How is it going to expand, and then how do you keep it expanded?
So the expansion is actually going to be very slow process. The overall expansion is going to take around an hour and a half, 2 hours. So it's pretty slow. And we're going to first expand it by introducing air through a very small port on the beam module's door or the hatch. There's a little small port, and we're going to connect a valve to that and introduce ISS air, the ISS atmosphere, into the module. So that'll start expanding the module, and in the first stages we will see the 2 ends, which we call the bulkheads, moving apart slightly, and then we're also going to see some radial expansion at the same time. Okay, so both things are going to happen, and then until the bulkhead goes to about 68 inches to 70 inches in length. Till that time we're going to really go slow expansion, okay, by introducing ISS air. Once it reaches its full length, which is around 70 inches bulkhead to bulkhead, then after that we're going to release the air tanks remotely. There are 8 air tanks inside beam, and the astronaut Jeff Williams is going to push a button and release the valves of the 8 air tanks, and that's going to introduce air into the beam module and take it to full pressure, which is 14.7.
Okay.
So that's the way it's going to be expanded.
So, to my understanding, I believe it's going to be expanded over the day passes, so that sunlight will be striking it and we'll be able to see it.
Yes.
Do you expect it to happen during the first day pass, which is about 90 minutes? Do you expect to go into a second?
So our effort, and I mean, obviously we'll try to finish it within the first day pass, but it may not happen within the first day pass, and then we'll have to take a break, okay, and then complete the expansion during the second day pass. So I think there is quite a good possibility we'll go into the second day pass.
Okay.
Yeah.
Once it is expanded, how much space will the astronauts have?
They will have 16 cubic meters of internal volume. I believe that's about 565 cubic feet. Hopefully I have my conversion correct. I just pulled it up from memory. But it's quite a lot of space. So it's about 9 feet in length. So you could comfortably stretch out, and the diameter, you can fit one person stretched out pretty comfortably. So it's not tons of room, but it's enough certainly to move around. And they're going to go in about twice a year and have experiments potentially that we're still working out.
Yep.
So yeah.
So just to relate the size of this thing, it's like It's like not as large as a master bedroom, but if you have like a master bedroom and 3 bedrooms, you know, the secondary bedrooms, it's about the size of a small bedroom, I would say. The size.
Okay.
Yeah. So fairly good size. Yeah.
So we have a lot of comments coming in, and it's really hard for me to keep up right now.
All right.
I saw
Exciting.
one about radiation protection. What?
All right.
How is this protected by radiation, and what are you testing for it?
So that's actually one of the things that we're going to collect data on, and that's part of the experimentation that we're going to do with this module. So we have 2 types of radiation sensors, and those were both provided by NASA, and they're going to collect the data, and Bigelow and NASA are going to look at the data, talk about it. So yeah, that's one of the things we're looking forward to examining.
Yeah, we have 2 types of radiation sensors on the our NASA avionics people designed it in-house. One is the active radiation sensor called the REM, Radiation Environment Monitor. We at NASA, of course, we use acronyms all the time, but that's the REM. And then we have the other one called the RAM, which is already being used on ISS on orbit. And those are passive radiation badges, and the on-orbit crew will take some of the RAM badges and stick it on inside beam. So with the combination of the passive and active radiation sensors, we're going to model the radiation environment inside beam and compare it with the rest of station. Because the interesting thing is both of these sensors are also present elsewhere on station, inside the metal modules. So if we get the same data inside beam and compare it with the environment inside the metal module, we will see relatively how much better or worse beam is with the existing ISS module.
Okay.
Does that make sense?
Yes, of
Yeah.
course. And so we got a question from Elijah's. Where will it dock? Meaning which part of the International Space Station?
So we call it berth, but its dock is pretty similar. But it is currently berthed to the Node 3 aft port. So it's the Node 3 module, the Tranquility module, and it's the port on the aft side of the module.
It's right by the cupola window where
Right by the cupola window.
where the astronauts take pictures with the handheld
Right.
cameras they have on board.
Yep.
So we're having a lot of questions come in about some of the experiments that we're going to be doing, and I know the astronauts are going to be going into beam at some point. So
Sure.
why don't we take a look inside the module?
Absolutely.
All right, let's go. So the astronauts are going to enter the beam module how many times?
Twice a year, is that right?
Actually, it's going to be slightly more than that. It's going to be 3 to 4 times a year, 3 to 4 times in 6 months. So it's going to be about 6 or 7 times a year.
6 or 7 times a year. So
Yeah, at least. Yes.
for the main part, will the hatch to beam be open or closed?
So during nominal operations, when I say nominal operations, the beam hatch of the door is going to be closed. Okay, but we are going to have continuous air exchange between ISS, the rest of ISS, and the beam module. So it's going to be completely ventilated, and the inside is going to be just like a living quarter. But we're going to close the hatch for just safety reasons and the fact that the astronauts are not going to live there permanently, right? They're going to just go in there.
Right.
But when they're ready to go inside, they're going to just open the hatch. They're going to unfasten their like 16 fasteners around the hatch door. They're going to unfasten that and then stow the door somewhere on station and then go in.
All right.
Yeah.
All right. So we have the beam right here. Why don't we go
and
inside?
the door is actually open.
The door is open this time, especially for us.
Yes.
All right. So for those of you just tuning in, we are getting an inside look at the Bigelow Expandable Activity Module. We're in Houston, Texas, at the NASA Johnson Space Center, and here we have a mock-up of the expandable module that's attached to the International Space Station right now. It launched on the Dragon cargo vehicle on April 8th on top of a Falcon 9 rocket. Was grappled by the International Space Station on April 10th. And on April 16th, they took it from the unpressurized trunk of the cargo vehicle and installed it onto the International Space Station. Now, in 2 days, they're going to be expanding the module to 4 to 4.5 times its size. That's May 26th, 4:30 a.m. Central Time, 5:30 Eastern. And we have 2 special guests that are with us talking everything you need to know about beam. Let's go inside.
All right, hi guys, welcome to beam.
All right.
So you can see how big it is now that we're standing outside. To give you some perspective, I'm about 5'7" with my heels, so it's pretty comfortable.
Yeah.
Not bad, plenty of room, and we are under the influence of gravity right now, so we have this lovely platform for us to stand on, but of course they won't be on a platform because they'll have 3 dimensions worth of space and no gravity to worry about. So give us a feel, what are we looking at on the inside? What are they going to be looking at on the inside?
So this is the inside of the air barrier, which normally when it's packed, when it goes up in the rocket, this air barrier is packed down with the rest of the layers of what we call our soft goods structure. And when the whole beam is pressurized, these walls move out and they actually become very rigid. So touching the walls is like touching the walls of your house. But this is exactly what they'll look like. You can see sensors on the walls, and I can let Rajib tell you a little more about what's on the walls.
The sensors, yeah. So that's the core of the technology demonstration, to collect the valuable data we are going to collect out of these sensors. And let me explain to you what kind of sensors we have. Right. So what you see here, these 3 boxes, this is what we call the aft bulkhead. Okay, and these 3 boxes is a marked DDS. It's called the deployment dynamic sensor. So these little transducers. These are load transducers. What they're going to measure when beam expands from the compact or the packed state to the expanded state. Remember the process I described? There is a little bit of load that is generated, dynamic load. Okay, and he's going to measure the dynamic load. So that data is going to be important for us when we design future expandables of larger size to kind of understand what loads are involved in the expansion, right? Then. So you see here, this is a wireless antenna, and by the way, all of the sensors are communicating to the outside, to the space station through the wireless antenna. Okay. Now let me go to the other kinds of sensors. You see these little dots here. We have 2 other sensors that's going. The astronaut is going to come there and stick just with a sticky bag adhesive. Those 2 types of sensors. The one is called the DIDS, or the Distributed Impact Detection Sensor. That sensor is there in case we have any micrometeor or orbital debris hit. That's going to detect the MMOD hits, okay? And detect how many MMODs, etc., and the environment and all that, okay? And then we also have wireless temperature sensors that's going to measure the thermal environment inside beam. And last but not the least, the most important, we are also going to have the radiation sensors that I talked about. So these are the different suites of sensors we'll have. So it's going to be an exciting time over the next 2 years collecting all this data. 2
years of collecting data, and I know the radiation tests that you're going to use, you do have to switch them out, correct?
We only have to switch the passive RAM badges.
Okay.
The ones I talked about. The active ones actually stay permanently stuck in the wall. But the passive badges, we have to switch it every six months, or whenever we have an increment crew change out. When the Soyuz comes back, we're going to bring them back because those have to be brought back to the ground for analysis.
Right, so they'll actually be brought to the ground, and you'll actually be able to conduct some testing while it's still being tested over the 2-year period.
Yes, absolutely.
Absolutely. Okay, so then what happens after the 2-year period?
So what we do is we need this berthing port. ISS needs this berthing port for other technology demonstration reasons. We would like to keep beam as long as we want, obviously. But once our useful time for data collection is over after the 2 years, the robotic arm is going to grapple beam from the outside, from Node 3 aft port, and then take it all the way down towards nadir. When we call nadir, is looking towards the Earth, and just release beam without any force, and beam is going to just drift away from station, okay? And that's called the whole jettison process, and it's going to take about a year or so to enter Earth's atmosphere and get burnt out in the process.
Wow.
So it's going to get jettisoned and burnt out in the Earth's atmosphere, but the entire process takes about a year. So yeah.
But it'll be 2 years of testing. That's plenty of information.
Yeah.
That's a lot of data to get.
Yeah.
We were talking about the astronauts coming in and out. can we describe a little bit what that looks like? How is it going to be whenever they do go in? Because the hatch is going to be closed, they're going to have to open it. Are they going to be wearing goggles?
So you wanna let me answer that, because it goes into the opposite arena. The first ingress, we call the first ingress, is when the astronauts are entering a new module. We have a flight rule that for protecting the on-orbit crew, we ask them to wear PPE, personal protective equipment. It's basically a mask and a goggle, and so it's essentially just to make sure that there is no fault or debris inside the module or anything like that, you know. But that's just the first entry. But on all subsequent entries, the astronaut's just going to go inside without any protective equipment. And let's see, you wanted to describe anything else while they do go inside, or?
What's it? I guess it's going to be dark, correct? Or is it going to be look like
well,
this?
the first time they go in, it's going to be dark.
Okay.
Okay. Because we don't have any lights permanently installed inside. Like this mock-up has lights, but it's not. Flight beam doesn't have lights.
Right.
But after the first ingress, the crew is going to install some portable lights from ISS. There is actually, what is not shown here, there is a crossbar. It's called the crew restraint bar.
It's right here.
Oh, I'm sorry.
Yeah, right behind you.
Yeah, that's right. It's right here. I missed it.
It's hiding.
So this crew restraint bar, you see they have these little posts, and we have a light on ISS. It's very, very bright light. Okay. That light just goes right here, and so once that light is fixed there, it's going to be pretty good.
So they'll have a pretty good view of
Pretty good view,
after
yeah.
the ends. So Lisa, let's talk about the perspective from Bigelow. What's what after this test? What's Bigelow looking into? What are they looking to do after this test? That sort of thing.
We're already working on our next program, which is called the B330, and I'd encourage you to go to our Facebook page, facebook.com/Bigelow Aerospace. Have a look at what we're doing. We're basically building bigger. So the beam is just small because of our constraints with the SpaceX rocket and trunk. But when we actually are choosing, a different launch vehicle, we have a lot more room to play with. So the 330, for example, is 330 cubic meters in internal volume, and to give you an idea, this is 16. So that can fit a much bigger crew.
Significantly bigger.
Yeah, have much more capability. Actually have some life support inside. The beam, it's just to test the structure. So there's no life support in here. We're just using the air circulation from station.
We are using life support, air circulation from station.
Mm-hmm.
So it's what I call passive life support.
Right.
But the environment inside beam is completely habitable, and we were able to prove that by a lot of analysis that we're going to get enough air circulation in there, and it meets the habitability requirements. Yeah. So it's pretty cool.
So that's the next step for us.
Yeah.
Very cool. So let's talk about the best part about Bigelow. The best part about expandable modules is the fact that you save a lot of volume. Just like the fact that the Bigelow was actually packed in the unpressurized trunk of the Dragon cargo vehicle. What other benefits does expandable modules provide that can be used maybe for a Mars mission or something like that?
Yeah, well, especially going to somewhere like Mars, the launch capabilities are even more reduced than to LEO, or what we call low Earth orbit, where the ISS
I would think
is.
so that's even
Yeah,
bigger
so
benefit.
your cost benefits and just your capabilities are, it's unimaginable how much you could do almost, with an expandable.
I'd like to also comment, Lisa, on the word mass. Right now, the way beam is designed, it doesn't really provide that much mass benefit compared to an equal size metal module. But as we mature this technology more into the future, we'll have more mass benefits because we'll find more efficient designs, right? This is an efficient design too, but this is over-designed for meeting requirements of high factors of safety. But as we mature this technology, we will be able to reduce those factors of safety and maybe get a lighter weight also. So mass will be definitely a benefit also in the future. And then radiation. We don't know at this point whether the radiation will be, that's why we are doing these radiation sensors to get the data. But once we get the data, it might look like the expandables are giving us some benefits for radiation protection. We don't know that right now for sure, but we'll see.
There's a lot of data to see, and we're really excited. We have 2 years of testing, and then obviously we have a gigantic Bigelow that's going to be coming in the future. Really looking forward to it. I wish we had more time because this is such an excellent conversation. And we do. Actually, after this, we're going to be doing a Reddit AMA at 5 p.m. Central, 6 p.m. Eastern. So be sure to tune into that, and we'll have these guys here answering even more questions. Sorry we weren't able to answer a lot, but I see there's a lot of questions and a lot of viewers on here right now. You can also tune in to the actual live expansion on NASA TV. It's going to happen at 4:30 a.m. Central Time, 5:30 a.m. Eastern Time on Thursday, May 26th. Be sure to check that out. I'd like to thank Rajib Dasgupta and Lisa Kauke for sharing with us all this great information about expandable modules and beam, and we're really excited to see this thing expand. Thanks, guys.
Thank you.
Thank you.